Hello everyone, this is Sir Said and hope you are doing well. Today we are going to solve another question of May-June 22 and the paper is 2-2. And straight away going to start from question number 1. In question number 1, you have to underline the SI base units. When the base units means ampere is the base unit and kilogram is the base unit, while degree Celsius and Newton is not the base SI units. In in part B, this is a beam. A block is placed at the one end of the beam and other end is fixed with the clamp. The block can oscillate up and down. The Young's modulus is E. K is the spring constant. T is the time period in fact, and M is the mass of the block. So this is the relation. Okay, there is a table 1.1 which gives the percentage uncertainties. On the next page, we have these quantities K, M, T and their percentage uncertainties. The actual value of E is also given. So to get the percentage uncertainty, we have to write the relation again. The relation is E is equal to K M T square. So if you see this relation, the power is here, so we have to use the power factor to solve this problem. So to get the percentage error or percentage uncertainty in E is equal to the power of K is 1, so 1 multiply with percentage uncertainty of K, that is 2.1, plus the power of M is 1, so 1 multiply with percentage uncertainty of M is 0.6, plus the power of T is 2, that means square, so 2 is multiplied with the percentage uncertainty of T, that is 1.5. So after solving this by using the calculator, the answer is 5.7%. So this is 5.7. The answer must be up to 2 sig fig. In the next part, you know that the actual value of E is given in the question. This value is 8.285 into 10 is per 9 and the percentage uncertainty is 5.7%. So to get the absolute uncertainty, we have to multiply these two terms and divide it with 100. Means the actual value is 8.285 into 10 is per 9 multiply with 5.7 and divided it with 100. The answer is 0.472 into 10 is per 9. So this absolute uncertainty must be one significant figure. So we may write it as 0.5 into 10 is per 9, and these two must have same decimal places. So we write it as, that is 8.285 8.2 and this is 0.5 and the combine is 10 is per minus 9. So it is one sig fig and both have the same decimal places. In question number 2, Direction of flow of water is shown with this arrow. This is a sphere, and the most important thing is that it is in equilibrium. It is in equilibrium. Equilibrium means the up and the downward forces and the right and leftward forces are balanced. Its angle is 68. The weight of the sphere is 32. Definitely the weight is acting downward. It's like this one. It's acting downward, 32 Newton. And the upthrust is definitely always upward towards the less pressure, and the value of upthrust is 280 Newton. Now the density of the water is given, and assume that the force on the sphere due to the water flow is in a horizontal direction, means there is no other vertical force acting, but there is some tension in this string, so we have to show the direction of the tension is in this way. So we divide the tension into the components. One of the component is here and the other component is along the weight, and these two angles are equal, opposite angle. This is 68. So this component is T sine 68. So this diagram shows that the downward forces are T sine 68 and 32. Their sum must be equal to the upward force because it is in equilibrium. So this is T sine 68 is 280 minus 32. So T is 280 minus 32 divided by sine 68, and by solving it through calculator, the answer is 267.47, and we may write it as 270 Newton. This is 270 Newton. So the tension is 270 Newton. In the next part, now you have to get, for the sphere, you have to get the volume. For the relation of upthrust, F is equal to delta P into A, and you know that it is rho GHA, also called rho GV. V stands for volume. If you are talking about the upthrust, this force is upthrust, and you know that the upthrust is given in the question. It is 280 Newton. So by substituting the values, it is 280 Newton is equal to the density of the water, because this pressure is because of the water. It is given 1 into 10 raised to the power 3 and 9.81, and V, the volume, is the subject. So by substituting all these values in the calculator, the volume is 0.029 meter cube. 0.029. This is the volume. So while getting the density, the relation is density is equal to mass over volume, and you know that the volume is given. So to get the mass by using weight, W is equal to mg, then m is equal to W by g, and weight is 32 Newton. It is fixed. 9.81 is also constant, so volume is known, and again by substituting the values, you can get the density is 110 kg per meter cube. So this part shows that the center of the sphere is initially at a height of 6.2 meter above the horizontal surface. So if we draw a diagram like this is the sphere, and from center of sphere to the top surface the height is 6.2 6.2 meter. But for new gravitational potential energy, you know the relation potential energy is equal to mgh. The potential energy is 77 and mg is the weight of the sphere, that is 32, and h, so h is 77 by 32, that is 2.4 meter. So initially the height was 6.2, and due to this new energy the height is 2.4 meter. And in the question you have to find the final height. So the final height is equal to 6.2 minus 2.4, so the answer is 3.8. For the time saving, I have write all the calculations on this paper. So moving towards next slide, and this is part D. The symbol for the equation gives the relationship between the tension in the wire. This is actually the force in the wire and the extension. You know that according to Hooke's law, F is equal to KE, and here we may write it as T is equal to KX. For the second part, before the sphere changed position, the initial elastic potential energy was this one. This is the elastic potential energy. And after changing the position, the extension of the wire is double. Yes, the wire become lengthy. So its new length is double to the initial length. Calculate the final elastic potential energy, means the elastic potential energy when the extension is double. So by using this initial elastic potential energy, you know the relation that energy is half kx square. This is half kx square. So this is 0.65 is equal to 1 by 2 kx square. And for the new energy E dash, this is half k, and now the extension is double, means 2x square, that is called 4x square. Okay, and you know that the value of this half kx square is this one. So it is 0.65 into 4. This 4 is here. So by multiplying, the answer is 2.6. So the answer is 2.6 joules. Moving forward, this question is related with the kinematics and energy. A man is standing on the wall and throw the ball vertically upward. So its initial velocity is 5.6, means when it comes at the top it will be like this one. The initial kinetic energy, the initial velocity is 5.6 meter per second. So it goes up and then falls down somewhere over here, and at the top its velocity was 0, and this height is 3.1 meter. So according to the given data, show that the ball reaches a maximum height above the ground is 4.7. So if we find this height h, and by adding this h with 3.1 you can get the answer. You know that the initial velocity is 5.6, means it has some kinetic energy. So gaining the height, this kinetic energy changes to the potential energy, means mgh is equal to half mv square. This m is cancelled with this m, and this h is v square by 2g, that is 5.6 square over 2g. So the answer is 3.1 and 1.6. So it is 1.6. So the total height is 3.1 plus 1.6. The answer is 4.7. It's shown. Now the man does not catch the ball and it falls downward as shown in this diagram. It comes over there. Calculate the time taken for the ball from its maximum height to the ground. It means when it falls down, maximum height to this surface, the time is required. So the whole height is known, that is 4.7. It's 4.7, the total height, and the initial velocity was 0. So we can use this equation, s is equal to ut plus half at square. This height is 4.7, initial velocity was 0, so it's 0, that is half 9.81 t square. So t is equal to 2 into 4.7 divided by 9.81 whole under root. So the answer is 0.98. 0.98 seconds. Hopefully you are getting the concept of this question. Moving towards next part. In this part, part C, the ball leaves the man's hand at t0. When the time was 0, means when the body was traveling upward and the time was 0. But at this time the velocity was 5.6. Yes, it's 5.6. Okay. And then at this top point the velocity becomes 0 from 5.6, and then it falls down like this one, and this height is now greater, so we can have the more velocity here, more than 5.6. So if we start from this point, maybe it is 5.6. So we have to draw a straight line. I'm not using any tools, I'm just going to draw this line by using a pen. This is a straight line, means somewhere over here. This is the top position, and then this velocity again increases to become at this point. This velocity is greater than 5.6. This velocity is greater than 5.6. So this is the correct shape of the graph. You can see that it has a negative and a uniform gradient. It means the acceleration is constant, and initially the velocity was 5.6, then it is 0 somewhere here at the center on the axis, and then this is the final just before hitting the ground. This velocity must be greater than 5.6. There is no need to write the value of this velocity on the axis, just the line shows that the initial and the final velocities of this whole travel must be different. So as I told you earlier, that this is the velocity time graph and the gradient shows the acceleration, so it is acceleration, and the type of the acceleration is negative and uniform. Moving towards next slide. This is part E. The man now throws a second ball with the same velocity and from the same height as the first ball. The mass of the second ball is greater. Now the mass is going to change. and assume that the air resistance is negligible. This is the most important thing, means there is no air resistance involved. For first and second ball, you have to compare the magnitude of the acceleration. The acceleration is same, the gradient is same, the acceleration is same, so it is same. The speed with which they hit the ball, this is actually the speed is same because there is no air resistance involved, so it is same as well. Now for this question, you have to write the state of the principle of conservation of momentum. You know the definition means the sum of momentum before and after collisions are equal in the absence of any external force. Sum of momentum before and after the collision are equal in the absence of any external force, means isolated system, or you may write that the initial and the final momentums are equal in the absence of any external force. So moving towards this part, here we have the two balls x and y moving along a horizontal surface as shown over there. You know that these balls are moving somewhere over here, and if we have to draw the vectors, the vector is like this one, and for this the vector is in this way. So we have these angles which are similar, the theta, and this is momentum 2.5 into 4.8, and here the momentum is 3 into 4. And if we divide these momentum vectors into the components, then we have the two horizontal components like this one. One is called 2.5 into 4.8 cos of theta, the other is 3 into 4 cos of theta. So the sum of these horizontal components must be equal to the momentum which is horizontally here. So we may write this equation. Actually, in the next part, the angle is required. The diagram is here, so I'm solving on it. It is 2.5 into 4.8 cos of theta plus 3 into 4 cos of theta is equal to, these two masses are added here, that is 3 and 2.5, 3 plus 2.5, and multiply with the velocity, that is 3.7. So this is 2.5 multiply with 4.8, the is 12 cos of theta plus 12 cos of theta. This is 5.5 into 3.7. So after solving, the theta is 32 degree. So this angle is 32 degree. Just going to repeat this question. Here we have two balls x and y. The masses are 3 and 2.5 kg, and these balls are traveling with some velocity 4 and 4.8. After collision, these bodies are in contact with each other and they are moving as a single body, and their velocity is now 3.7. And if we divide these components of the momentum vectors, then we have these two horizontal components. Their sum must be equal to the momentum after the collision. So by substituting these equations, we can get that the angle is 32. So in the next slide, actually this angle is required, so all the calculations must be written over here. And now by calculating the kinetic energy, State explained whether the collisions of the ball is inelastic or elastic. So we have to write the kinetic energies before collision and the kinetic energy after collision. If the kinetic energies are equal, then the collision is elastic, perfectly elastic, otherwise not. So initially the mass was 3 and the velocity is this one. For the other, the mass is 2.5 and its velocity is 4.8. So the sum of these kinetic energies is 53 joules. After collision, the kinetic energy is half. The combined mass is 5.5 and the velocity is 3.7. Whole square is equal to 38 joule. These two kinetic energies are not equal, so it is inelastic collisions. And it was question number 4, and that's all. Thank you very much. Good luck.